Hey everyone, my name is Fabrice, and today we're going to be looking into the question of whether neuron coverage is a meaningful measure for testing deep neural networks. Let's get started. So most of you that have made your way to this video have likely heard of neuron coverage before. You've read about it in a paper, you've used it in your research, perhaps even in an industrial setting. You've used it to justify the launch of a DL system into production. But just in case it's a new concept, let's take a minute to review what it is and why people care about it. The idea of neuron coverage was originally inspired by code coverage within traditional software engineering. Code that gets executed by a test has the potential to reveal buggy behavior more than code that is never run. And coverage tells you the proportion of code your tests actually execute. You can measure this in terms of lines of code, paths of code, etc. But what neuron coverage is doing is it takes that basic premise and extends it to the machine learning setting, where instead of counting code statements, we count the neurons in a DNN that are covered or activated by a set of test inputs. Now, since neuron coverage was proposed in 2017, it spawned a slew of related works, expanding on the idea of neuron-based coverage metrics. In addition to the original paper's Deep Explorer tool, we have Deep Test, Deep Gauge, Deep Road, Deep what have you, all collectively garnering over 1,000 citations, a lot of high-impact work. As a quick illustration, let's take a look at how neuron coverage is actually calculated. So here you can see along the top inputs to a single layer neural network, which has 5 neurons in the second row. Each neuron has unscaled activations on top of the scaled activations in parentheses. Neuron coverage will count a neuron as being covered if its scaled activation exceeds a certain threshold. For the sake of simplicity, let's assume a threshold of 0, meaning that anything that's activated at all is counted. Here, we can see that this test input results in 3 out of 5 neurons being activated for a coverage of 60%. It's a pretty straightforward idea / calculation that no doubt contributes to its popularity. So now for why people care. This goes back to the age-old question of how we build trust in the things that we create. Safety and reliability concerns are holding back many applications of DL systems, from self-driving cars to autopilot in drones and commercial airliners, to even medical diagnoses. All of these safety-critical systems require, even sometimes by law, evidence of correct behaviors, and neuron coverage is designed to guide your testing efforts towards a set of potential defects for eventual correction. But is it actually successful in doing this? Is it truly a meaningful measure for testing deep neural networks? So we return to the titular question, and in order to evaluate it, we conducted an extensive empirical study focused on computer vision, where we created over 2,000 test suites, reflecting a broad cross-section of potential projects. We consider 8 different types of DNNs with a variety of architectural properties, some of them having one-dimensional convolutions, two-dimensional convolutions, fully connected layers, high and low capacity networks, and so on. I'd also highlight that we considered both classification and regression datasets, MNIST and CFAR10 being for classification, the Udacity self-driving car challenge dataset for regression, where you predict steering angle from images of road conditions. There are a number of other variables at play, and I'll refer you to the paper for those. Now, each test suite contains 100 inputs uniformly distributed between the classes. We then perturb those inputs using adversarial attacks, the CW attack and the PGD, extended with a diversity-promoting regularizer that increases neuron coverage while still inducing errors on realistic inputs. We'll talk more about that in a moment. Then we calculate some key criteria related to each test suite. The first being defect detection, which is the number of defects the suite is able to induce, naturalness, which is how realistic the inputs are, and finally, output impartiality, which measures whether the test transformations that we made to the suites resulted in any strong biases that favored particular test classes over others. We argue that all 3 of these are important factors to consider when designing a meaningful test metric, and we see if neuron coverage is positively and strongly correlated with them. Finally, we conduct a follow-up experiment to see if it's possible to predict if Any classes may be overrepresented in a test suite modified with neuron coverage maximization as a guiding objective. But first, let's talk about how we increased neuron coverage in a new way. So we did this by creating an entropy-based, diversity-promoting regularizer that can easily be incorporated into just about any algorithm that relies on incremental optimization. For our study, we chose to extend the CW and PGD attacks, as I mentioned before, because they're two of the most popular adversarial methods in the literature. They both jointly maximize loss, minimize the norm distance from the original inputs, and now, because of the regularizer, maximize neural diversity. It does this by measuring the KL divergence between a uniform distribution and the actual distribution of neural activations for a targeted set of layers in the DNN. The greater the divergence, the higher the penalty. So let's take a quick look at its impact. On the left, you can see the unscaled activations for a subset of neurons in a particular model layer. Only about 10% of them are activated beyond the 0.2 threshold. After regularized perturbation, the same inputs now activate 52% of the neurons above the same threshold, representing a significant increase in neural activity. So that's how it works. But why invent a new approach if others have proposed their own methods for increasing neuron coverage? The answer is that we wanted to have faster batch transformations that consider more than one input at a time, can make more free-form changes to the inputs, whereas previous methods generally considered a limited set of transformations, like shears and adjustments to brightness. And we also wanted to remove the overhead of differential testing, which was integral to the original Deep Explore approach. With models becoming more and more expensive to train because of their growing size, techniques that can operate on a single model are increasingly important. So now let's talk about how this technique enabled us to build test suites with a variety of defects and how they correlated with neuron coverage. Our first key criteria is that of defect detection, which we reframe as the attack success rate of the augmented adversarial attack. Quite simply, the ASR is 1 minus the perturbation accuracy of the model on the test inputs. The definition is inherently classification-oriented, so for our driving data set, we bin the continuous steering angles to permit for a consistent analysis. So what's the first hypothesis that we investigate? It is that neuron coverage is both strongly and positively correlated with defect detection. And what did the results show? So what we see here is the distribution of results of the correlations between neuron coverage and defect detection. Following standard procedure, the correlations are binned into strongly, moderately, and weakly negative and positive groups, with NA representing cases where a correlation could not be drawn at all because there was no variation in the number of defects. Highlighted in white are those results that supported the hypothesis, of which only about 3% did. Even more concerning is that in over 50% of the results, we observe a negative correlation, where increasing neuron coverage saw a decrease in the amount of defective behaviors found. So, taking a look at a sample of the results from the CW attack on all three datasets, we see that the convolutional 1D-net exemplifies the NA outcome. It had a 100% attack success rate, no matter what level neuron coverage was. And the other models show their respectively mixed results. We would refer interested viewers to the paper for more visualizations like this. So the next key criteria that we use to evaluate the meaningfulness of neuron coverage is naturalness. Often an implicit goal in testing, we think it is important to explicitly consider how natural your tests appear to be. Unnatural inputs can deviate so significantly from the target data distribution that they become impossible for even human oracles to handle properly. So it shouldn't be something that we hold against an AI model either. Basically, the value of a defect increases if it's realistic, decreases if it's not. Since we're working on the image domain, subjective spot checks wouldn't be suitable. They're unreliable, unscalable, and two people can reasonably disagree on the tricky to define term of naturalness. Fortunately, related research into generative adversarial networks, or GANs, has yielded more or less objective metrics that are used to automatically quantify naturalness. We make use of two of them in our analysis, the inception score, where higher scores indicate increasing realism, and the Frechet inception distance, where lower scores indicate more realism because the distance from the original inputs are smaller. Now, both metrics are tuned upon an inception DNN trained on ImageNet data, which corresponds to a wide array of natural object scenes, making the metrics themselves useful for data coming from similar distributions. Unfortunately, MNIST is arguably not natural in the same way, where we have highly pre-processed numerical digits centered against a blank background. So for this part of the analysis, we exclude MNIST and focus exclusively on CFAR10 and the driving dataset. So what's the hypothesis here? As of before, the hypothesis is that neuron coverage is both strongly and positively correlated with naturalness. Now for the results. When it comes to naturalness, our second hypothesis has even less support, with only about 1.5% of the results being strongly and positively correlated, while almost 70% were negatively correlated to some degree. Increasing neuron coverage seems to correspond to more unnatural test suites. Now, moving on to the charts, looking at a sample of the CW attack results on the CFAR data specifically, we see that the general relationship between increases in neuron coverage and the change in naturalness, again, increasing FID is not actually a good sign. Those are counted as hurting the naturalness in the correlation calculations. On a similar note, within the driving dataset, we see some more mixed results, with the overall trend being that increases in neuron coverage correspond to decreases in naturalness. So finally, let's talk about the third key criteria, output impartiality. This newly proposed idea emphasizes the importance of what the model thinks it sees in the inputs and measures the degree of skew introduced in the test generation process. Ideally, a model will be tested with a variety of inputs, and this is pretty easily controlled by manually enforcing an equal distribution of test types or classes at the beginning. Each one of these classes has certain combinations of features that characterize it, and the model learns to detect those features for prediction purposes. However, when an objective like neuron coverage maximization is being used to guide the creation of new test cases, class-specific features can be blended together, and thus affect the post-transformation distribution of model predictions. We measured the shifts in that distribution via Pailou's evenness, a well-regarded measure of ecological biodiversity applied for the first time to ML output behaviors. In this context, we refer to it as output impartiality, or OI for short. So, same as before, we calculate this OI score for each test suite and determine its correlation with neuron coverage. However, we also conduct a follow-up experiment that seeks to predict exactly which classes are likely to be overrepresented in the output predictions of the newly generated test suites. This is done based on the observation that each class has a different average neuron coverage, and therefore neuron coverage maximization, which is how it's normally used in praxis, is more likely to favor the features of classes with higher average baseline neuron coverage. But first, let's look at the main hypothesis of the correlation study. As before, we hypothesized that neuron coverage is both strongly and positively correlated with output impartiality. Here we see that the correlations are once again unfavorable for neuron coverage. Less than 5% of the results show a strong positive correlation with output impartiality, which is more than any other key criteria, but it's still not a ringing endorsement. So lastly, let's take a look at the sample of results showing a mixture of relationships. Again, we'll refer you to the paper for more visualizations like this. As for the follow-up experiment, I'll explain the experimental setup. The first thing to recall is that neuron coverage is different based on the class of the input. That means that different classes have a different baseline activation, how much they're exciting the network. For example, a network may activate more strongly when shown images of dogs than it does for images of fish. First, we pick 10 instances of each class in MNIST. So we have 10 zeros, 10 ones, and so on. For each grouping, we calculate neuron coverage at a particular threshold, starting with 0. Whichever class has the highest neuron coverage is ranked first, and whichever class has the lowest is ranked last. All the others are somewhere in between. To get a robust measure of neuron coverage's preference for certain classes, this process is repeated with different thresholds, 0.1, 0.2, etc., until 0.9. The ranks at each step are then averaged to find the classes that were consistently over and under stimulating the DNN, and the highest ranked class would then be predicted to be the most common class in the output distribution of a random test suite. So the results showed that class 8 consistently had the highest neuron coverage, with an average rank of 2.1 across all thresholds. When perturbing a test suite with neuron coverage maximization as an objective, the resulting output distribution showed a significant bias towards the 8 class, likely because the features belonging to the 8 class could be most easily incorporated to attain those increases in neuron coverage that satisfy the objective. Theoretically, this would make it more likely that other class features are not as well tested, like those belonging to classes 6, 1, and 9, and ultimately compromise the effectiveness of the entire testing effort. So that concludes the main experimental results of the paper. Let's quickly discuss a few key points related to the comparison with previous work and neuron behavior conceptually before wrapping up with key contribution summary. So it's worth wondering whether the results we found are a consequence of our diversity-promoting regularizer and that other techniques might have more favorable results for defect detection, naturalness, and output impartiality. In order to address this concern, we repeated smaller scale correlation studies with both Deep Explore and Deep Test. For Deep Explore, we were unable to find a single correlation that supported any of the 3 hypotheses, and for Deep Test, only one correlation supported the hypothesis for output impartiality. The triangulated agreement between these 3 techniques suggests that our findings are generally applicable to neuron coverage and are not really dependent on the technique used to increase neuron coverage in the test suite. Furthermore, both tools had a tendency to produce severely unnatural tests that we would argue should not be considered valid. For example, the first example comes from Deep Explore, modifying an input from the driving dataset until it is completely white and lacking useful information. The quote-unquote correct steering angle is indicated in green and the incorrect model prediction in red. The next 2 are from Deep Test and show similarly questionable utility. So then there's the matter of inherent neural behavior. Firstly, research into neural visualization has shown that neural features are not discrete and regularly blend concepts together, as you can see along the top here. Their power lies rather in the complex patterns of activations that collaboratively work to map inputs to outputs. It is therefore unclear how any metric that considers the behavior of individual neurons could give meaningful information about the behavior of the DNN as a whole. Even if we assume independent, discrete encoding of features in the neurons of a DNN, is it still desirable to maximize their activations, and that is, maximize neuron coverage? If we think of coverage in a binary sense of activated versus dormant, and each neuron detects some feature in the input, then there are 2 to the n possible combinations of neuron activations in a model with n neurons. Keeping it simple, let's assume that there are 2 neurons, one that detects cars and the other that detects pedestrians. The NC maximizing objective is fully satisfied by an image that contains both a car and a pedestrian, but remains silent about the other 3 possibilities that might be crucial for testing. Overall, it seems like neuron coverage maximization as an objective focuses on one direction at the expense of other valid directions. So, wrapping this up, in this work, we propose a novel regularizer that can augment your favorite adversarial attacks to increase neuron coverage as well. We conducted an extensive study of the relationship between neuron coverage and some key test criteria, them being defect detection, naturalness, and output diversity. And most importantly, these empirical results invoke skepticism that neuron coverage is actually a meaningful test metric. Lastly, if you're interested in getting your hands on any of this code that we've done for the analysis, we've all made it available on GitHub, and you can have the link in the paper as well. So this is the team that produced this research: myself, Ling Xiao, Gulzar, Chen Chen, and Miriam. And we all thank you for taking interest in this work. Until next time, take care for now.